Alright, in this video we're going to introduce homogeneous ordinary differential equations. We are going to set up the theoretical framework, and then in the next video we're going to look at some examples. Okay, notice that in this video we are assuming that you're already familiar with separable ODEs. So if you are not up to speed with that, please first check our video on separable ODEs. Right, so we're going to start with the definition. So a continuous function of two variables f, x, and y is said to be homogeneous of degree n in x and y if plugging in lambda x and lambda y in the place of x and y gives us a lambda to the power n times the original function, where n is a real number. Lambda is also a real parameter. Okay, so let's look at some examples of how this works out. So in these examples we're going to determine whether the given functions homogeneous or not. Okay, so determine whether f is homogeneous. In part A, we are going to look at f is equal to, suppose we have x y squared plus 3x squared y. Okay, so is this function homogeneous or not? So what we're going to do is we are going to plug in lambda x, lambda y in the place of x and y. So x is going to be lambda x, this is going to be lambda y all squared, 3 times lambda x squared times lambda y. Alright, and then if you remove the brackets, in the first term we're going to have lambda cubed xy squared. Here we're going to have 3 lambda cubed x squared y. So this thing is lambda cubed xy squared plus 3 x squared y. Now, so as you can see, this is exactly the same as the function we started with. So this is lambda cubed times f of xy, and so the f is homogeneous of degree 3. Okay, just a little tip here. So note that for polynomial functions, okay, so whenever f is a polynomial function, it's going to be always homogeneous if the powers of x and y in each term add up to the same number. Okay, so if f is polynomial, so polynomial f is always going to be homogeneous if power of x plus power of y is equal to the same number for every term, for all the terms. Okay, so for instance, if you look at this one, if you look at the powers of x, so here it's going to be 1 plus 2, which is 3. Here is 2 plus 1, which is 3. So that means straight away, for instance, 4x squared y squared minus 6xy cubed, straight away this is going to be homogeneous, because the power of x and y add up to 4 here and add up to 4 here. Okay, so that's going to be homogeneous straight away. However, x to the power 6 minus 3 x squared y to the power 4 plus 7 xy to the power 4, this one is not going to be homogeneous, because for the first term the sum of the powers is 6, some of the powers is 6 here, but some of the powers is 5 here. So this one is going to be not homogeneous. All right, so that's going to be useful going forward. So let's do another example. Suppose in B we have f of xy equal to y plus the square root of xy. So again, we're going to plug in lambda x for x, lambda y for y. So the first term is going to be lambda y. Then the second term is going to be the square root of lambda x times lambda y. Okay, if we remove the brackets inside the square root, it's going to be lambda squared xy. So this is going to be lambda y plus lambda into the square root of xy. So this is lambda into y plus square root xy. I can see that the term inside the brackets is now what we started off with as f. All right, so let's give you 2 examples to have a go at, or maybe we're going to give you the examples at the end. Okay, so let's just go on to the next section. So there is a theorem which is a connection, gives us a connection between the idea of homogeneous functions and ordinary differential equations of the first order. All right, so this theorem states that if functions m and n are homogeneous of the same degree in x and y, then the ODE m dx plus n dy equal to 0 can be reduced into separable form via the substitution y is equals to xv, where v is a function of x. So what this theorem is saying is that if you transform from the xy frame to the xv frame via the substitution xv, so y is a function of x and v is also a function of x, then this equation here is going to be separable. So this is provided, of course, m and n are homogeneous. So let's see a proof of this, and then after that we will look at some examples. Okay, so we are going to start by rewriting the equation, the ODE. So first we rewrite, so m dx plus n dy equal to 0. We are going to rewrite this in the form dy dx is negative, so that is going to be negative m over n. Okay, so let's call this our equation asterisk. All right, then the substitution y is equals to xv is going to give us the following. So first of all, we're going to rewrite the derivative in terms of v. So, and using the product rule, so dy dx, if we differentiate this side, then on this side, if we use the product rule, so if we differentiate x and keep v fixed, and then we're now going to keep x fixed and differentiate v, so that's what the derivative is going to be. Then if we plug in to the these terms m and n, remember these two terms are homogeneous. Okay, so so let's say since m and n are homogeneous of the same degree, okay, of the same degree, we're going to assume that that degree is n. Okay, then what's going to happen is it means m of xy, then we are going to plug in xv in the place of y, because that's what the substitution is giving us. Then so now x here is going to be like play the role of lambda, so that's going to be x to the power n m of 1v, because m of 1v is just going to be a function of v, so let's call it p. So that's simply x to the power n times p of v. Similarly, n of xy going to be n of xv, which is x to the power n n of 1v. N of 1v is just a function of v, which is let's call it q. Okay, now so then we can we're now in a position to rewrite this equation asterisk in terms of v. The left hand side is going to become this, the right hand side is going to be given by the negative of this term divided by that term. So therefore the ODE, this one, becomes, so on the left hand side we're going to have v plus x d v dx. So that's what the derivative becomes in terms of v. Then on the right hand side we've got negative m over n. After the substitution, m becomes x to the power n. So x to the power n p of v divided by x to the power n q of v. The x to the power n cancels out, so that cancels out. Then p of v divided by q of v is just another function of v. Let's call it r of v. So let's say negative r of v here. So we now have v plus x dv dx. Now this is going to be separable now. If we bring r to the left hand side, I've got v plus r of v there, and then plus x dv dx is equal to 0. Then what we are going to do is if we divide everything by this term, we're just going to rearrange really. So if we first multiply by dx and divide by x, basically this is what we're going to have. Okay, maybe let me do that step by step. So I'm going to multiply by dx and divide by x. So it's going to be dx over x v plus r of v here, plus dv equal to 0. Then after that, this is going to be dx over x plus dv if I divide everything now by v plus r of v, and there we are. And this is now of course separable because this is a function of x only and this is a function of y only, so which is separable. All right, so yeah, let's summarize. So basically what we have said here is that if m and n are homogeneous of the same degree in x and y, then this equation here, ODE, m dx plus n dy equal to 0, can be transformed via the substitution y equals xv into the equation dx over x plus dv over v plus some function of r equal to 0, of which this form is separable and so can be evaluated using the method seen or explained in our video on separable equations. Okay, so before we come to the end of this video, let's just give you 2 exercises where you want to test whether each of these functions is homogeneous, exactly the same way as we did in the previous function. So suppose we've got f of xy equal to ln x minus ln y minus 2, and b, suppose we've got f of xy equal to x minus y minus 2. So if you'd like to just pause the video, have a go at these, and then when you press play, then you will find our solution to these two examples. All right, so we hope that you have had a go at these two functions, determine whether they are homogeneous or not. We're now going to scroll down to our answers. So first one, if we plug in lambda x and lambda y for x and y, then by the properties of logs here, lambda x, ln xy becomes ln lambda x becomes ln lambda plus ln x. This one is going to be ln lambda minus ln y minus 2, and then the terms involving lambda are going to cancel out because we've got plus here and minus, and so here we are back to the same function we started with. So it means f is homogeneous of degree 2. This one, using the tip we gave you, is a polynomial of degree 1, but the powers of x and y add up to 1 here, and 0 here. So straight away this one is not going to be homogeneous. But if you go through the algebraic process, you'll find that this is not homogeneous. Right, thanks for watching this video. Please subscribe to if you find it useful, to get prompted whenever we post new stuff. The next video is we're going to work through ODEs, which can be solved using the homogeneous approach. Thank you.